The next topic in complex numbers is it possible to say something like, 3 to the imaginary power? Is that something that's even allowed on the calculator? Well, it turns out that if you do type it into the calculator, it does not crash the calculator, but it gives an actual answer, which in this case is about 0.45 plus 0.89i. And if I raise something else to the imaginary to I get 0.77 plus 0.64i. And there's a fairly easy to remember rule for how to raise numbers to imaginary powers. It's a very hard thing to derive, and in this video I'm going to tell you what the rule is and see. You could look at this and see if these answers have anything in common that might be interesting. If you want to pause and think about that, what do you notice about these two answers? We're going to also be able to raise things to 2, 3 to the 3 plus 4i power, things like that. But for now, just raising it to the I power. This is what the calculator says. If you notice anything about these, you can pause and think about that. Okay, maybe you thought to convert these into trigonometric form, and if you did, you would notice that it ended up being around 1 cosine 63 degrees plus 1 I sine 63 degrees, whereas 2 to the I ended up becoming 1 cosine 40 degrees plus 1 I sine 40 degrees. So one thing they seem to have in common is that the R value is 1 for both of them. But where does this angle come from? Well, we'll find that out by looking at a different base. So for 3, it was 63 degrees. For 2, it was 40 degrees. And of all the bases, the one that kind of reveals what's going on is if you raise the mathematical constant e to the I power. If you pop that into the calculator, you get 0.54 plus 0.84i. And if you change that to trigonometric form, you get 1 cosine 57.3 degrees plus 1i sine 57.3 degrees. Is there anything special about 57.3 degrees? Why don't you think about that? You can pause and think about that. Okay, welcome back. Well, 57.3 degrees is equal to 1 radian. So e to the I is actually 1 cosine 1, that's in radians, no degree sign, plus 1 I sine 1. And if you take e to the 2i, you end up with negative 0.42 plus 0.91i, which actually turns into 1 cosine 114.6 degrees plus 1i sine 114.6 degrees, which happens to be cosine of 2 radians plus I sine of 2 radians. And this leads us to the general rule that e to the theta I will always equal cosine theta plus I sine theta. Now, different bases we'll talk about in a minute, but for now, that's the key rule. And we're not really proving it as much as just noticing that it seems to be true. If we test it out with raise e to different multiples of I. But if it is true, we can get some cool things out of that. For instance, if I change theta into some number not like 1 or 2, which I don't know cosine and sine of offhand, but if I change theta to something like pi over 6, and it would be cosine pi over 6 plus I sine pi over 6. So by choosing angles that I know what their cosine and sine are, angles in radians, pi over 6 is like 30 degrees, so it's radical 3 over 2 plus I times 1/2. So I could actually get the exact answer, 1/2 I, to e to the pi over 6I. Another one, e to the pi over 2I. That's cosine of pi over 2 plus I sine pi over 2. Cosine of pi over 2 is 0, and sine of pi over 2 is 1, so it's 0 plus I is just... Oops, that's not true. Actually, it is true. So that equals I. And one other one that's notable is e to the pi I is cosine pi plus I sine pi. Cosine pi is -1, and sine pi, sine of 180, is 0, so it just becomes -1. So that's interesting. I could raise e, which is irrational number, to an irrational and imaginary power, and ends up with a real number. That last one, though, is pretty famous. E to the, usually we put the I pi like that. E to the I pi equals -1. If we rearrange that by adding 1 to both sides, we get one of the most famous equations in all of math. E to the I pi plus 1 equals 0. It unites the seven of the most important symbols in math. 0, 1, plus, equals, pi, e, and I, all together in one equation, one relationship. What if the complex number has a real part? You could think about that. Push pause. Welcome back. In that case, we can split this up into e to the 3 times e to the pi over 6I, which turns into e to the 3rd cosine pi over 6 plus e to the 3rd I sine pi over 6, which becomes e to the 3rd times radical 3 over 2 plus e to the 3rd over 2I. So we could even two complex numbers that have a real part by splitting it up using the reverse of the x to the a times x to the b is x to the a plus b rule. Now you might wonder, what if it's not e to the I? What if it's 3 to the I? You can pause and think about that. Welcome back. You can rewrite 3 as e to the ln3. E to the ln3 is equal to 3 because ln3 is the number you have to raise e2 to get 3. So if you raise e to the ln3, you'll get 3 to the I. So it's e to the ln3I, which is cosine of ln3 plus I sine of ln3. Well, ln3 in radians apparently is about 63 degrees. And that's why in the warm-up we saw that happen. We could just leave it like this, assuming radians, but if you wanted to change it into degree, you could actually just type it into the calculator here also and get the answer. Let's do that, and you'll get 0.45 plus 0.89I. Make sure your calculator is in radian mode. And as a last kind of cool thing to end this unit, so you've seen one real famous formula, e to the I pi plus 1 equals 0. We could actually use this idea to calculate out the unthinkable. What is I to the I power? Well, we can't do what we did before with 3. We can't change I into e to the ln because maybe we can't take ln. But what we can do, remember back here, we saw that if I put pi over 2 in for I, pi over 2 for theta, I end up with I. So I can, instead of I to the I, I'll do this thing to the I power. E to the pi over 2I. Well, now when I raise a power to a power, I multiply the exponents. So I get e to the pi over 2I squared, which is e to the negative pi over 2, which is 1 over e to the pi over 2. Anyway, you could type that into the calculator, and you end up with about 0.2079, which is very surprising because I'm taking an imaginary number, raising it to an imaginary power, and I'm ending up with a purely real number. And that's what I to the I is, 0.2079 approximately. Well, that's going to do it for now. The last thing you might wonder is, why is this all true? Why does, why is it true that e to the theta I is equal to cosine theta plus I sine theta? And that's a very hard question to answer. I think the only thing I'll say about it is, if you take two numbers like 2e to the 5i times 3e to the 4i, you would expect to get 6, because 2 times 3 is 6, e to the 5i plus 4i, which is 9i. On the other hand, if I change this thing into 2 cosine 5 radians plus 2i sine 5 radians times 3 cosine 4 radians plus 3i sine 4 radians, the multiplication rule for complex numbers says I should get 6 cosine 9 plus 6i sine 9, which kind of agrees with this answer, although it's not really clear why should e be that would be true no matter what the base was, even if it wasn't e. But we'll leave that for a more advanced math course, why this rule is true. For now, you have the ability now to raise numbers to imaginary powers using this rule at some point.